Hello and welcome back to BME 2315. In today's lecture, we're going to be talking about root finding. So as the biological example in this section, we're going to be talking about calcium signaling. So as you may have seen already in your physiology course, calcium is critical for contraction of muscle cells. So basically calcium enters from these ion channels and is released into the cytoplasm where it binds to myofilaments and initiates contraction. So because of its importance, calcium is at the heart of many attempted therapies for heart failure. And so one example of this is gene therapies that are designed to express proteins that buffer calcium, with the idea is that decreasing calcium would be beneficial for heart contraction. And what they find is in this stained area here, this is the area where they injected this adenovirus into the heart. And then they measure the function, the pressure developed in the heart, either in a control example or on the right-hand side when this calcium buffer is overexpressed. And they find that overexpressing this calcium buffer leads to stronger contractions and also stronger relaxations. So calcium is really critical, and it's a leading candidate for heart failure therapies. And so based on this importance and the role of calcium buffers, we want to look at how we can solve this mathematically. So this equation right here represents the different states that calcium can be in. We have a term for the total calcium. We have a term for the free calcium. This term is the amount of calcium bound to protein 1. This term is the amount bound to protein 2. And this is the amount bound to protein 3. And in your problem set, we'll go into more detail to explain what's going on here. But basically, the fact that there's a square or a fourth power here indicates that there are multiple calciums that are bound to each of these. So this is an equation that relates the free calcium and the amount that's bound to different proteins in your cells to the total calcium. And so what we need to do here is to solve for the free calcium and see how that is affected by the different buffers. In order to do that, we need to rearrange this equation to be F of calcium is the total minus the free minus each of the bound states equals 0. And the roots of F of calcium are solutions, which means that would tell us what the free calcium is when part of it has bound to these buffers. Okay, so this is you're going to get into that problem on the problem set. So now let's take a look and dive into root finding and look at how we would actually do these calculations to calculate the roots of a solution, the roots of an equation. So in the last section, we were talking about linear systems, and a linear system is nice and easy to calculate the roots, like this. And we can calculate that by Gaussian elimination, right? You're also familiar with a quadratic equation which is nice and simple and has a simple analytical solution to it. But a lot of the more realistic problems are more complicated than quadratic. And so, for example, if you had a fourth order polynomial or a trigonometric function or something more complicated, something that perhaps looks like this, how would you find the roots of this numerically? And so how would you find the roots of this numerically? And so basically we're going to be looking at solving where f of x is our function, and we're going to try to find the values at which x equals a solution when we've got f x equals 0. So there are two main different strategies for root finding. The first are bracketing methods, and the basic idea is that we'll have a lower guess and then an upper guess, and we'll gradually converge on the solution and to find the root of the function. So that requires two initial guesses, and is a kind of a slow but sure way of finding the root of this equation. The second are what are called open methods, and they're called open methods because we just start with one initial guess, and we'll try to iterate from there and try to find the solution to the equation. What we'll see is that this method is faster than the bracketing methods like bisection, but is less guaranteed to actually find the solution. Okay, so we'll be talking about that method in the next lecture. For now, we're going to be focused on exactly how this bisection method would work. How do we converge on the roots of our function f of x equals 0? So here's the outline of the bisection method. First, we're going to choose a lower and upper guesses for the root, such that the function changes sign over the interval. So I'll draw this out here. So we have an XL and an XU, and we'll say that the 0 line looks like this. So, and in this case, we know that the XL and XU change sign over that interval. And then we're going to estimate the root XR by being halfway in between XL and XU. Like that. And then we're going to do a couple calculations. We're going to be, first, we're going to be looking at the product of f of XL and f of XR. Okay, and in this case, we can see that it's going to be less than 0 whenever they're on different sides of the 0 line, okay? And so if that's true, then that means that the true solution is in this upper interval. Okay, and so we're going to then reassign f of xr to be xu, our new upper interval, and then we'll repeat this process. The other way that this could work would be if the 0 line is more like this, so that f of xr is just above the 0 line right here. And in this case, we're going to take the product again of f of xl and f of xr, and when we see that when they're on the same side of the 0 line, then their product is greater than 0. And so if their product is greater than 0, then we know that the true root is somewhere on this lower interval. Okay, and so if it's on a lower interval, we're going to say that x of r is going to become the new f it's going to become the new XL, and then we'll reiterate this process again. So this process works pretty well. There are a couple of cases that you should be aware of that might run you into trouble. One is what happens if all the points are above the 0 line. So if you think about like this, then XR will converge to XU. Okay, because there is no root in between these, and so that this algorithm will get tricked a bit and think that the root is at XU when there actually is no root. And the other case is what happens if there are multiple roots. Okay, and then with multiple roots, XR will depend on the shape of F. So that's not a good thing, because we want a foolproof method, and this is going to depend exactly where you put XL and XU. Right here. So basically, we hope that the situation is one of them, something like one of the options on the right, where we either find that a true solution is in the lower interval or in the upper interval. Okay, so that gives us a loop, so we can keep iterating, but we can't go on forever. We need an objective termination criterion. And while we'd like to use the true error, we don't know the true answer, right? Because we don't know the true root. So as an alternative, we'll often use an absolute approximate relative percent error. And so this is just like our approximate error equation that we've used before, except note it here that we're using absolute values to define this error. And second, this bisection process is slow but steady. And so that's one of the things that's nice about it, is that we know that it's going to converge kind of gradually over time. And so because we're always having the interval size, we can derive the following equation that tells us how much approximate error you should get after n iterations. So where x0, delta x0 is our original interval size, and n is the number of iterations. Okay, so this shows us that the approximate error will get smaller and smaller as we do more iterations. Okay, so now with that the basic framework for how we do bisection method, let's apply this to an example. So say we've got this function right here, e to the minus x, and we start out with a lower and upper bound at 0 and 1. Okay, so the first thing that we can do is calculate what xr should be. XR will be halfway in between them, so it would be at 0.5. Okay, so it would be about here. And then we multiply f of xl, which is this point, times f of xr, which is this point. And notice how they're both positive values. And so their product would be greater than 0 rather than less than 0. And so we say no, it is not less than 0. And so then that means that the true solution is on the upper upper interval, and so we're going to now borrow the root to be the new lower interval, because we've eliminated the lower interval, okay? So that goes there, and the percent error is not applicable on this first iteration. Okay, so then now we're going to repeat this process here, where we say, okay, halfway in between 0.5 and 1 is 0.75. That's our guess at our root right now, okay? And then we multiply, and we say that 0.5 and f of 0.75, that's this point and this point, you see that they are on opposite sides. So their product would be less than 0. So there's a yes there, okay? And we find that the approximate error going from 0.5 to 0.75 is 33%. Okay, and so since this was found to be on the lower interval, that means that the new upper value is coming from the root right here, 0.75. This one stayed the same. And so, and then finally, we can find that the XR is halfway in between 0.5 and 0.75, so 0.625, okay? And so that corresponds to a 20% approximate error. So let me just write down just a reminder. That in bisection method, the new root is always halfway in between the XU and XL. Okay, so this shows us a few iterations of this process. To give you more examples, on this next slide, I show what happens if you would repeat this process. And so first off, on the right-hand side, you can see that the approximate error keeps getting smaller and smaller. It is gradually honing in, and that this diagram on the left over here shows us how, like on the first one, how we localized it to the top half. Then on iteration 2, we localized it to the left-hand segment, and on iteration 3, we localized it to the left-hand segment again. And so it's gradually having the area in which it's investigating on each iteration. So the key points from this bisection lecture are that bisection allows us to find roots of an equation between the lower and upper guesses. Bisection is slow but steady, and it has the interval at each step. And so while this approach was slow but steady, it required 2 guesses, a lower and an upper guess. And in the next section, we'll be looking at open methods that don't require bracketed guesses, that they require just 1 guess and may be able to find the root faster. A disadvantage of them will be that they may not find it at all. So thanks. Hope that is useful to you, and I'll see you next time.